Now we are going to discuss about the pipeline. The pipeline is the effective way of organizing concurrent activity in a computer system. What is concurrent activity? So we can increase the throughput. That is, throughput is the number of instructions executed per unit time. So if you go for a sequential execution, if for example, if we are able to execute a 10 instruction, if we are able to execute a 10 instruction per unit time, but if you are using a concurrent activity, we may execute 20 instructions per unit time. So the throughput has been increased. The throughput has been increased by using the concurrent activity. At the same time, you need to be very clear. The amount of time taken to execute each instruction cannot be reduced. If it is a sequential activity, so it is a sequential instruction execution. We have a 3 instruction. So each instruction needs 2 clock cycle to complete its execution. So definitely each instruction needs the same clock cycle to complete its execution. So in total, so 6 clock cycles. So if we use the concurrent execution, okay, so in here also each instruction need 2 clock cycle. Okay, each instruction need 2 clock cycle, but the throughput is not the throughput is different. Here, for example, the unit time is 6. So by using within a 6 clock cycle unit time, we can execute a 3 instruction in a sequential execution. But in concurrent, it will be different. We see how it will be, how it increases the throughput. That we see now. Okay. Here, this is the hardware arrangement for a concurrent execution. So we have a separate hardware unit for instruction fetch and separate hardware unit for instruction execution. Intermediately we have one buffer here. So the instruction which has been fetched in the clock cycle 1 has to be stored in the buffer. So in the next clock cycle 2, the execution unit take that instruction from the intermediate buffer in the same time, in the second clock cycle. This instruction fetch unit will fetch the next in the instruction fetch unit will fetch the next instruction I2. Okay, so this is the hardware organization for the concurrent execution. Now I show you how it increases the throughput. See, consider this is the rows are instructions, instruction 1, instruction 2, instruction 3. The column are number of clock cycle. At clock cycle 1, the instruction 1 has been fetched. At clock cycle 2, the instruction 1 go to the execution unit. In the same clock cycle 2, the instruction 2 has been fetched. Because we have a separate hardware unit for instruction fetch and instruction execute, so this fetch unit in clock cycle 2, the fetch unit fetches the instruction 2, the execution unit executes the instruction 1. Then come to the third clock cycle. In third clock cycle, the instruction 3 has been fetched by the fetch unit. The execution unit executes that instruction 2. Okay. Then in the fourth clock cycle, instruction 3 is getting executed. If we have a instruction 4, that might be in a fetch stage. Okay, in clock cycle 4. Now you see each instruction had two clock cycle to complete its execution. Instruction 1 needs 2 clock cycle. Instruction 2 needs 2 clock cycle. Instruction 3 needs 2 clock cycle. So instruction 1, 2, 3 each need 2 clock cycles to complete its execution like a sequential execution. Here also the instruction 1 needs 2 clock cycle and the instruction 2 needs 2 clock cycle. The instruction 3. But the difference is here it is a concurrent activity. While the instruction 1 is in execution, the instruction 2 is in a fetch stage, right? So at the end of clock cycle 3, two instructions have completed its execution. At the end of 4 clock cycle, 3 instruction has completed its execution. But see here, at the end of the 4th clock cycle, so it is a clock cycle, it is a clock cycle, it is a clock cycle 1. So clock cycle 1 here, 2, 3, 4, 5, 6. At the end of the 4th clock cycle, in a sequential execution, only that two instruction has completed its execution, but here all the 3 instruction has been executed. At the end of the 6th clock cycle, you consider 6 clock cycles per unit time. So at the end of the 6th clock cycle, if it is a sequential execution, 3 instructions alone has completed its execution. But here at the end of the 6th clock cycle, 5 instruction might complete its execution. That is the different. So by using the concurrent activity, it not reduces the execution time taken to execute per instruction, but it increases the overall throughput. Number of instruction executed per unit time has been increased. Okay, that is pipeline. Okay. Now this is also another example for instruction execution. So here again, so the instruction is the previously the example what we have shown is that the instruction having only the 2 clock cycle, instruction having only 2 phase, instruction fetch and decode phase. Here we have a 4 phase, instruction fetch, decode, execute and write phase. So each instruction need 4 clock cycle to complete its execution. So instruction 2 is in the decode stage, instruction 1 is in the decode stage, 2 will be in a fetch stage. Come see here at clock cycle 4, the instruction 1 will be in a write stage, instruction 2 is in the execution stage, instruction 3 is in the decode stage, instruction 4 is in the fetch stage. So here in the same clock cycle, 4 different instructions are concurrently executed, but all are in different stage. This is not parallel processing. It is a concurrent processing. Okay. So the difference between the parallel processing and concurrent processing. This is the example for concurrent. If it is a parallel execution, it will be different. See here. So fetch, decode, execute of 1 and W. So clock cycle 1, 2, 3, 4. Like that all the 4 instruction will be in a same stage if it is a parallel processing. Okay, but the concurrent processing is different. So to execute the parallel processing, that many if you want to execute a 4 instruction parallelly, you need that many hardware units to perform that. You need 4 hardware unit for fetch. You need a 4 different hardware unit for decode, 4 different hardware unit for execute. So here in the parallel processing, all the 4 instructions will be executed parallelly. It means that all the 4 instructions will be in the same stage at a single clock cycle. Here the instructions are executed in the concurrent processing concurrently, but all the instructions are in different stage, not in the same stage. That is the difference between the concurrent execution and parallel execution. Here we have a one hardware unit, okay, but each hardware unit are executing different instructions. That is the concurrent execution. In parallel execution, if you want to execute 4 instructions parallelly, that many hardware units you should have. Okay, that is parallel processing. This is the hardware arrangements for um, 4-phase instruction execution. So in the first clock cycle, instruction will be switched and stored in the intermediate buffer. Then in the second clock cycle, we have a decode unit. It decodes the instruction. It also fetches the operands in the second clock cycle itself. Keep that in mind. Then at the end of the second clock cycle, the operands are stored in the intermediate register buffer B2. Then third clock cycle, the execution operation will happen. That execute the hardware which is used for execution will be used here. After end of the third clock cycle, the executed result has been stored in the intermediate buffer B3. Then the results are written back to the register or a memory location, whichever is the destination location for that particular instruction. So these buffers are called as interstage buffers. This is for 4-phase instruction execution. The previous one is we only have simple one, 2-phase, which each instruction is divided into 2 phase. Here each instruction has been divided into 4 phase. Okay, that's all about pipelining. Now you might have clearly understand what is sequential execution, what is concurrent execution, what is parallel execution. All three are different. Okay, next we see hazard. What are all the issues in pipeline? The first one is the data hazard. First, before we discuss into the hazard, we see what is data hazard. We see what is hazard. Any condition that causes the pipeline to stall due to some issues. Any of the instruction, okay, any of the stages in the pipeline is idle for some situation. It is not doing any of the operation. The pipeline is idle. That is called as stall. Any condition that causes the pipeline to idle or stall, okay, that is called as hazard. Okay, there are 3 types of hazard. Now we discuss the first type, that is called as data hazard. So the data hazard is any condition in which either the source or the destination operands of an instructions are not available. So the data is not available for execution. Data is operand. The operands are not available for instruction execution. As the data are not available, the instruction execution is getting delayed. So it makes the pipeline to be idle for some time. Okay, that is called as data hazard. See this example here. So see here see here the data is not available in the for the second instruction. The data is not available in the clock cycle 3 and clock cycle 4. The data is available, the data or operand both are same, which is available in the fifth clock cycle only. So the pipeline is idle for 2 clock cycles. The pipeline has been stalled for 2 clock cycles. So that is called as data hazard. I show you some example. Consider the two operations. A is equal to 3 plus A and B is equal to 4 into A. Consider the value of A is equal to 5. So the output of the first operation is A. 3 plus 5, that is 8. The output of the second operation, now it takes the value of A is equal to 8. The 4 into 8, 32. If you execute in these two operations in a sequential manner, one by one, but if you execute these two operations in a concurrent manner, okay, so the A will be 3 initially, but the B, while the second operation will take the same A and 4 into 3, it will be 12. So it gives the wrong result. So here there is the two operations are called as dependent. What it is? It is dependent. Okay. So if there is a dependency in these two operations, or you can also consider it as an instruction. If the two operations are consecutive operations in the program, it is called as instruction. The two operations are in the program, it is called as definitely instructions. If the two instructions are dependent, definitely you should execute in a sequential manner, otherwise it gives the wrong result. So the a value which has been taken in that particular time is, before it updates the value of A, the operation 1 updates the value of A. If the operation 2 reads the value A, it generates the wrong result. Consider here the next two set of operations. A is equal to 5 into C, B is equal to 20 into C. Here it gives these two are independent operation, right? So there is no dependency. These operations or these instructions can be executed in a concurrent manner. Now I see this two instruction, multiply the value which is available in the register R2, R3 and store the result into register R4. That is the first instruction. The second instruction is add the value which is there in the register R5 and R4 and store the result back into the register R6. Now you take this two instruction and map here. Okay. So at clock cycle 1, the multiply instruction has been fetched by the fetch unit. At clock cycle 2, the instruction has been decoded and the operand R2 and R3 has been fetched. Okay. Now in the execution stage, the it multiply R2 and R3. Okay, and it update the value of R4 in the clock cycle 4. This is what happening in the first instruction. Go to the second instruction, add. So the fetch unit fetch the instruction add R5, R4, R6 in the clock cycle 2. In the clock cycle 3, it decodes that instruction and it needs the operand R5, R4. Okay, but the R4 will be ready at the end of the fourth clock cycle. Okay, if it reads the R4 here, it leads to the wrong answer, right? So, this operand fetch of the, especially the fetch of the R4 value has been delayed till clock cycle 4. Then only the R4 is ready. So in the R5, again it's go and fetch the R4. Okay, that's what there is a delay because the R4 is not updated till clock cycle 4. It has been locked by the instruction 1. Okay. So at the end of the fourth clock cycle only, the R4 value has been updated by the multiply instruction, that is the instruction 1. Till clock cycle 4, the instruction 2 cannot fetch the R4 value. R4 value is not ready. So at the in clock cycle 5, again it has to fetch. So it needs the instruction 2 needs to wait till clock cycle 4. So at clock cycle 5, it fetch the R6. So in the clock cycle 6, it executes that add instruction 2. Then it writes them, update the value R6. Here it do R5 plus R4. Okay. So 2 clock cycle delay has been happened in the instruction 2 due to data unavailability. Okay, the operand. See what happened to instruction 3. Instruction and the clock cycle 3, the fetch unit is free. The fetch unit fetches that instruction 3. But as the decode unit is not complete its decoding operation of instruction 2, it is idle. it didn't complete that work. It was keep on waiting for operand R4. So the instruction, the decode hardware unit is not available. It is also waiting to get the hardware unit. The decoding hardware unit has been released by the instruction 2 at the end of the 5th clock cycle alone. So the instruction 3 get the decode unit only in the 6th clock cycle. Then it gets remaining as you. Okay, like that for instruction 4. The instruction actually, if there is no delay, no issue, the instruction 4 should be fetched at clock cycle 4 itself. But that fetch unit is not available. Okay, so it is holding that I3, right? So it has to keep on wait the instruction 3 to release that fetch unit. So it gets the fetch unit by 6th clock cycle. Okay, so due to the problem in instruction 2, so all other instructions in the pipeline has to wait. So if there is a stall, if the pipeline is idle, it will affect all the instructions. Not affect it, all the instructions need to wait in the pipeline. Okay, that is called as data hazard. Okay, I hope now you can understand what is hazard, how to, what is called as data hazard. Okay, now data, how we are going to overcome, what is the solution for improving the delay or avoiding the delay if there is a data unavailability. Consider this. Okay, we are using the technique called as operand forwarding. So here in operand forwarding, so what you need to do is, so after executing the instruction, so on the end of the third clock cycle, the instructions are available in the intermediate buffer. Okay, the results are available in this intermediate buffer. In the fourth clock cycle only, it will be written to the register or a memory location. So here we have a one more path called as forwarding path. Okay, so see here the instruction 2 needs the operand for execution in the third clock cycle. What it does is, so it takes that operands from here and directly giving to the execution unit. So it avoids the delay. Sometimes it minimizes the delay. In some of the cases, it avoids the delay. Here it avoids the delay. At third clock cycle, the operands are given directly to the execution unit. It's not going to the decode unit. Okay. So in the third clock cycle, it is ready. It taken and given to that second instruction. So by using this operand forwarding, so that you have a extra data path between that intermediate buffer B3 to that execution unit. Okay, so while decoding itself, we come to know that this instruction is depending on the previous instruction. So it takes a decision that the data has been, the dependent data has to be forwarded to the execution unit. Here also it is like in a 3-bus architecture. So the results are go to this multiplexer. So if whether it is a source value or the previously executed value, any one has been taken to the ALU. This is the 3-bus architecture style. Okay. So the solution for data hazard is operand forwarding. So we have rearranged made some changes in the hardware part. So how we are handling the data hazard in software? To handle the data hazard in software, we have to insert the no operation instruction. So the control hardware delays in the example. So the control hardware delays by reading the register R4 until the clock cycle 5. So for 2 clock cycles, it has been introducing the no operation instruction after clock cycle. After this 2 clock cycle, the value of R4 will be ready, right? So by using that no operation instruction, we can handle the data hazard. So the who will do that? The compiler can introduce that two clock cycle delay which has been needed between this instruction 1 and instruction 2 by inserting this two no operations, no operation instruction. Okay, it won't do any operations. Okay, next one, side effect. Here, sometimes the data dependencies encountered in the are explicit. See here in this example, we definitely the data dependencies are explicitly known because the name of the register is available in the instruction itself. Sometimes an instruction changes the content of a register other than directly named as a destination register in this previous instruction. Here the R4 is a destination, but it will be a source instruction for the next instruction. That is the problem here. So if it is explicitly known, there is no issues. But in some time, in some instruction, it won't be, it changes the value of that some registers which has been not named explicitly in the instruction. So that time, so when a location other than the explicitly named in an instruction as a destination operand is affected, that instruction is said to have a side effect. Okay, example, push pop. So that will be auto increment or auto decrement or whatever it is. So we are not those operand affected is not explicitly mentioned in the instruction itself. That but it do some changes in that operand. Okay, which affect that instruction execution. Okay, this is called as that kind of instruction is said to have a side effect. Okay, so that's all about data hazard. Okay, so before getting to that hazard, you should know what is pipeline, what is sequential execution, what is concurrent execution, and what is parallel execution. Okay, thank you.